So I have the honor of introducing Professor Bernhard Scholkopf. He is the director of Max Planck Institute for Intelligent Systems in Berlin, right, since 2011, or 2001. And also, currently, he is a distinguished visiting scholar in a little company called Amazon. And is a member of German Academy of Science and a co-editor of a flagship paper, or journal, Machine Learning, called the Journal of Machine Learning Research. His research focused on many aspects of machine learning, especially in kernel learning and transfer learning. And the first time I heard about Bernie's existence was when I was asking people who is expert in transfer learning, because I want to prove him or her wrong. So everybody pointed to Bernie and said you should meet him because he's the expert. But then before I got a chance to meet him personally, I found out that he is ahead of me. And he figured out that to do transfer learning properly, you got to do it with causal models. So by the time we met, he was already in the commonsensical camp, as we can hear today. And last week, Professor Scholkopf, together with his co-authors, that was Jonas Peters and Dominic Danzig, received the ASA, which American Statistical Association Prize for Causality Education in Statistics, for their book named Element of Causal Reasoning. And without further ado, let's give warm welcome to Professor Scholkopf. Now it would like
So thank you very much, Yuda, for the kind introduction. And thank you all for coming here. It's quite an audience and a beautiful lecture room. So I hope I'll try to speak loud enough. That would be a good start. I hope I can live up to the setting, to the surroundings, to the introduction, etc. And tell you a little bit about causal learning and about why I think this is the future, or maybe one topic we definitely have to understand if we want to make progress towards artificial intelligence. Is that, I guess I'm coming in and out. It's not bad? Okay, you give me a signal if it gets too quiet. I don't have a very loud voice. So I work at the Max Planck Institute for Intelligent Systems, and we are interested in intelligent behavior, and in particular, we're interested in understanding the organizing principles of intelligent behavior. And of course, there's lots of different forms of intelligent behavior. Here we have a blood cell chasing bacteria. This is a frog trying to catch a fly. These are some humans that exhibit sort of impressive dynamic behavior. This is called parkour. And here finally, we have some humans that engage in a highly sophisticated form of collective behavior. And I think if you look at this diversity of the kind of behavior that humans produce, it's clear to us that current machine learning cannot produce all this. Current machine learning has done some impressive things, and maybe one of the most impressive, or one that captures the imagination also of the general public, has been this work of the company of DeepMind. Or maybe, first of all, it has been this work on object recognition, where we now have systems that can beat humans in certain settings, deep networks, and then the work of DeepMind that has sort of used similar approaches to learn reactive systems that learn to play video games at a level that's sort of comparable to humans. So all these things were rather impressive, and they published this in Nature. And at the time, I was asked to write or to comment on this, sort of whether this is impressive or what's new about it or what's impressive. And I thought a little bit about what these recent advances mean and where they come from. And I think there's certainly multiple trends at work here. And I think we know about most of them. First of all, we have massive amounts of data, and massive amounts of data usually means it's either from simulations, which is the case in this video game application, or we have a large-scale human labeling, such as done by Amazon Mechanical Turk, etc., or by the internet companies that pay people to label data. We also usually in these applications have rather high-capacity machine learning systems. So these could be deep neural networks with millions of parameters. We have GPUs and other forms of compute power and can do large scale or massively parallel computation. And moreover, and maybe more importantly from my point of view, since I have a theoretical background, something that we usually don't stress in practice is that in all these cases, the settings are usually IIDs, or independent identically distributed data, or we somehow make them IID. So either we collect data which is exactly from the right distributions, or nothing changes between training and test time. That's can be achieved by just having humans label the data, or we kind of make the data IID, and this is, for instance, done in this DeepMind system, where all the data that this network is trained on is constantly being stored, and then occasionally the data is permuted and retrained, and they liken this to some kind of sort of dream phase and memory replay during sleep. So we effectively make the system look a little more IID, because that's what we know how to handle. And if the data are IID, then we know that there are learning systems, and even the nearest neighbor classifier is an example of that. We know that there are systems that are universally consistent. So we know that in the limit we can, so that there are various classifiers, deep learning, support vectors, etc., for which we have theoretical results that we know that tell us that in the limit we get the best possible performance. So in this sense, it shouldn't be so surprising for us that we see this now happening in practice, but maybe it's not the whole story. And in a way, this talk is about this assumption of IID and what happens if you violate this. And I'd like to motivate with this simple example, which I already used before I had my current affiliation, and I also made sure to remove all the names. So just consider this an abstract example of how machine learning is used in the internet. And I should also say this is an example from a few years ago. The system, I think, is different now. It doesn't give you this recommendation anymore, but at that time, it was the case that if you looked for a laptop rucksack, then the website recommended that you should also buy a laptop to go along with the rucksack. And that's kind of funny, because you probably already have a laptop. Otherwise, you wouldn't be looking for the rucksack in the first place. So in some sense, intuitively speaking, we would say the laptop is the cause and the rucksack, or wanting the rucksack, is an effect. Now, on the other hand, if you tell me whether a customer has bought or has put a laptop or has a laptop in their shopping cart, it certainly reduces my uncertainty about whether he or she also has a laptop rucksack in the shopping cart, and vice versa. And in fact, it does so by the same amount, and this amount is called the mutual information. So if you look at this kind of, look at it from this point of view, there's no directionality between these two things, the rucksack and the laptop. On the other hand, the directionality certainly is there if we look at the physical mechanisms that generate the statistical dependence in the first place. For instance, and these we may not understand these mechanisms, but we can think of a mechanism that makes you want to buy a rucksack once you have the laptop. Maybe the mechanism involves you thinking about the laptop falling down and breaking, or maybe you even have such experiences. But physically, there might be such a mechanism that generates this dependence in the first place. And if we now recommend an item here, then in a certain sense, this constitutes an intervention into a system. So we intervene in a system, and this means we leave this IID setting where we're just passively observing something that always comes from the same source. We no longer work with what's called the observational distribution, but we work with a distribution where certain variables or mechanisms have changed, and this is what causality studies. Now, let me talk about causality, and the next slides I have two pictures of the giants of causality, and amazingly, they are both connected to UCLA. So this is the first one, Hans Reichenbach. Was a very interesting character. Since we're at UCLA, I should say a few words about him. He was a philosopher. He did a PhD in probability theory, which was largely written without having an advisor. I think he had a hard time finding someone who would give him a PhD for his work. His first academic appointment was at the University of Stuttgart, which I mentioned because I was born in Stuttgart. And he was then subsequently hired to the physics department, which was also somewhat unusual for a philosopher, a physics department in Berlin by Einstein, Planck, and von Laue. He lost his job in 1933. He was of Jewish ancestry on his father's side, and I think he was also a socialist. So he left Germany, went to Turkey, became the head of the philosophy department in Istanbul. And in 1938, he moved to UCLA, and I think he was instrumental in making this the place to be in philosophy. So in Istanbul, yeah. I just mentioned it. Yeah, so he first went to Turkey, and then he came here from Turkey. Actually, quite a few Jewish scientists from Germany went to Turkey. It's not so well known, but this was a home for many of them. And so he was the PhD advisor here, for instance, of Hilary Putnam. So anyway, Reichenbach, he came up with this thing which is now called, or which I think maybe already he called the common cause principle, which, for instance, can be read about in his book, The Direction of Time. And this principle says if you find two observables to be statistically dependent, then there exists a third one that causally influences both of them. And this third one can be chosen such that it screens the first two from each other. In other words, given the third one, the first two become independent. So this means in the generic case, it will look like this, but it has special cases. Z could coincide with X or with Y. And so, for instance, if we assume that X is the frequency of storks let's say, I think there's a nice data set of the European countries, so the frequency of storks in a country, and Y is the frequency, the human birth rate, frequency of babies. So it turns out there's a strong correlation between the two. So if the stork brings the babies, then this would be the correct explanation. If the babies somehow attract storks, this would be the correct explanation. If there's some other variable, such as economic development, that causally influences both the frequency of storks and the human birth rate, then this would be the correct explanation. Now, the crucial insight is that without additional assumptions, we cannot distinguish these three cases based on observational data only. So the class of distributions over X and Y that can be realized by these three models is the same in all cases, which means that a causal model genuinely contains more information than a statistical model. And causal models, as pioneered by Yuda Perl, can be written as functional causal models. So in the simplest case, we think of a set of observables that lie on a direct acyclic graph. We have arrows that represent direct causal links. And on each variable, we have each variable is computed as a function of its parents and a noise variable or an unexplained variable UI. So the UIs are independent random variables, jointly independent. And it turns out this kind of a system entails, and so if you specify the distributions or factorizing distribution over these noise terms, this implies a joint distribution over all observed variables, xi. And this distribution inherits some interesting properties from the structure of the graph, and these properties can be specified, or some of them can be specified by the so-called causal Markov condition. And this condition says that when conditioned, so look at this green point here, when conditioned on the parents, on the red ones, this variable becomes independent of its non-descendants. And as a side note, this is also one way to write what's called a graphical model. So a graph together with with the joint distribution over all the variables is sometimes called a graphical model. Now, the nice thing about this representation is that it's immediately obvious how to model interventions. If you intervene in a system, you simply change some of these functions, and then you no longer get the observational distribution, but you get what's called an interventional distribution. And you can do the same thing for other kinds of changes, even if you don't explicitly intervene, but something else changes, something changes in the environment, then we typically assume that some components of this model here change and others don't change. Now, one of the profound questions of causality is, of course, what if we only have the observational distribution? Can we recover this graph, or can we recover something about the graph without intervening in the system? And the answer is that if we are willing to make certain assumptions, such as this faithfulness assumption, then even though we may not be able to infer the one graph that explains the data, we often can infer a class of graphs that contain the correct one by something called conditional independence testing. And so I told you before that this structure implies certain conditional independencies. So this is a ternary relation that sort of connects at least three things to each other. So we can infer something, and the idea, so I won't tell you in detail, I mean, you have the experts here, and many of you may know about this anyway, but I just want to give you an intuition. So you have such a system, and now you have an independent noise that's fed in at each node. So they are jointly independent, so you can think of it as a kind of noise probes that you put in. Now you let those noises propagate through the graph, and these noises determine the different observed variables. And whether an observed variable knows something about a noise term just depends on whether the noise term is upstream or not. And then now you have your joint distribution over all observables, and you can ask conditional questions of the form of what does this variable know about this one that it doesn't already know from this one. So in a way, now you try all possible combinations of three variables, and intuitively it's clear that then this should tell you something about the graph topology, because as these noises propagate through the graph, the initial independence gets broken. So you suddenly have quantities that depend on multiple noise terms. So you start with the independence. As the independence gets lost, it picks up information about the topology of the graph. Well, that's a beautiful idea. And in practice, there are some things that make it difficult to do this. And one of them, which is sort of something that is particularly natural for me as a machine learner. My background is machine learning, so we are obsessed with finite data results. We're obsessed with making assumptions about function classes, etc. So one thing is that so far, amazingly, all this is true independent of what functions we have on these nodes. So these functions that sit here, they could be arbitrarily complex. But in machine learning, we all believe that we must make assumptions on function classes. If functions are too complex, then you cannot work in practice. So in practice, and actually by now, meanwhile, there are results on this. One can prove that if these functions are complex, and if we have only finite samples, then actually conditional independence testing can become arbitrarily hard. So that's one problem. And the other one is that if we have only two variables in the graph, which in a sense you could say is kind of should be a trivial special case, then it's actually particularly hard because there are no non-trivial conditional independence statements to make if there's only two variables. Because conditional independence always requires three quantities that you want to connect to each other. So the two variables case is kind of elusive. And the idea, in a way, something that addresses both of them, is to think about that not just the graph leaves a footprint in the noise and in the dependent structure of the noises, but also the functions that you here have on the node, in some sense, leave a footprint. And so over the last 10 years or so, it still feels like a fresh area for me in causality, but if I think back, actually by now I've worked on it for 10 years. So in these years, we've thought a lot about the role of the functions, or maybe more generally about the causal conditionals, and what assumptions we need in order to address the two variables problem. And this is the cause-effect problem, and it's also a classical problem of philosophy. this guy here, the philosopher Nietzsche, he called it reason's intrinsic form of corruption. So the error of mistaking cause and consequence. And I want to tell you about some assumptions that are relevant here. So one assumption I want to introduce with this picture here. And this is a picture of what's called a Bechet chair. So when you see this object, it has these two components. And this is a place where you look through. So when you see an object or any object, your brain makes the assumption that the object in the world and the mechanism by which the information about the object enters our brain and is processed are independent objects of nature, you could say. Now, this assumption we can violate, in this case, by looking this particular hole, which then enforces that the projection which you see depends on the structure of the object. So if you violate the independence assumption, you look through this particular hole, then perception fails because you suddenly see a 3D structure which in reality is not there. So this assumption that normally the independence does hold, I think is a good one, because most of the time it's satisfied. So if I look at an object, my brain assumes that the object is independent of the vantage point, it's independent of the illumination, so there shouldn't be any accidental coincidences. There shouldn't be 3D structures that suddenly line up in 2D, or even though they're different in 3D. Or there shouldn't be shadow boundaries that coincide with texture boundaries, etc. And in vision, this is called the generic viewpoint assumption. And also, if I move around an object, so my own vantage point changes, so the mechanism from the object to my perception changes, I will naturally assume that the object itself doesn't change. So there's an overall a model that generates my percept. And this model has two components. One is the object, one is the process. And I will assume even if the process changes, the model itself is invariant. So if we have a sort of a model consisting of multiple components, we will normally assume that changing one of them does not affect the other one. So that's a form of an invariance, which is also connected to this independence that I mentioned before. And I think this invariance is what allows us to infer 3D information even if we only use one eye. For instance, by a process called structure from motion that computer vision people use. So let's assume that we have a causal generative process that's composed of autonomous modules that do not inform or influence each other. So I'll give you another example from a different domain. This is a data set that we got from the German Weather Service. And in this case, we have the altitude of weather stations in different places in Germany. This is the highest mountain, it's 3,000 meters. And then you have a lot of weather stations in low places. And here you can see the average annual temperature. So you can see that the higher you go, the colder the place gets on average. And if I ask you now, what of the two, suppose you had to decide what is cause and what is effect, the temperature or altitude, I think most of us, after thinking for a while, would probably say, I can see why the altitude would have a causal effect on the temperature. Maybe the air pressure goes down, etc. Maybe there's more wind. But I don't quite see why the temperature should directly cause the altitude of a place. So people would think it's reasonable to think this is the causal direction. Temperature causes altitude. And maybe if you know, let's say you don't believe me, I try to convince you somehow. I could go about this in different ways. I could say, well, let's just try an intervention. So let's build something that will raise a city of LA by 1 kilometer up. And then we measure for a year and we will find that it gets colder. Then maybe you're convinced, but that seems impossible to do. So maybe I'll just say, well, let's do a hypothetical intervention. Let's imagine we raise LA, and then we talk about physics, and I will try to convince you that the air pressure goes down, and maybe there's some other mechanisms. So I will refer to physical mechanisms that maybe we both learned about in school, that we both believe in, and that we believe hold independent of whether we manipulate the altitude of a place. So that argument, if it convinces you, would be related to this independence principle that I talked about before. And similarly, it's also related to the invariance that I mentioned before, because maybe it could be, if I look at Switzerland and Austria, they're both in the Alps, so they have a different sort of profile in terms of the altitude of the places, but maybe they founded their cities in different places, but maybe you would still believe that this kind of mechanism that produces the temperature given the altitude would be the same, even though maybe the Swiss ended up building their cities higher up for cultural reasons. I don't know. So we have these different aspects, and we think one can think of this independence as a general principle. And I'm not claiming that we are making this up. So there's a lot of precedence to this kind of thinking. I think maybe the only new thing is here we have tried to formalize this. I'll say a little bit about this later, in terms of algorithmic complexity or Kolmogorov complexity, and we're trying to use it for causal inference, and I'll also say a little bit more about that later on. So there's this general independence that I think is at the basis of a lot of causality, and it has to do with whether one can intervene somewhere. It has to do with modularity, invariance, and it has also various other interesting implications. And I'll try to show you 2 examples. So in a way, I think also, I won't go into detail on that, also the independence of the noise terms in a structural causal model can be viewed as an instantiation of this principle. I won't talk about this one because that's the one that's used in causality methods. I'll try to say a little bit more about this. So I'll give you 2 examples. The first one is based on the independence of cause and mechanism. So that's the 2 variable case. So if we look at a structural equation model, it reduces to this trivial setting here where we have a cause that has its noise term. Since it doesn't depend on anything else, we identify it with the noise term. And then we have an effect, which is a function of cause and its own noise term. And now we want to assume, or we want to formalize what we mean by saying that the conditional of effect given cause, so this mechanism, is independent from this other mechanism. Now this other mechanism, since it doesn't have any parents, it's just identical to the distribution over the cause. So in which sense are these 2 objects independent? And we will make it even easier. We don't have any noise. So let's take a structural equation model without any noise here. So we just have some input distribution over x. We apply a function. We then, via this function, the input distribution implies an output distribution. So we have these 2 distributions. So we observe the joint distribution, and then we're asking which of the 2 is cause and which is effect. So that seems to be a difficult problem. But if we are now formalizing what we mean by independence of the cause distribution and the conditional, which in this case is just that function, then it turns out that this problem becomes solvable. So the idea will be that if this function knows nothing about the shape of this distribution here, then you will generically find that the output distribution does know something about the function. The function will leave a footprint in this distribution because wherever the function is flat, the output density will have a large mass or higher values. So if this shape here knows nothing about this shape, then it turns out that the value of the output density will say something about the slope of this function here. So there will suddenly be, if the independence holds true here, it will be violated between these 2 objects. And we can formalize this, and I won't go into great detail, but we can formalize it in a very simple setting. We consider the unit interval. We assume the function f is a bijection, monotonic. It should be bijective, otherwise it kind of becomes asymmetric to begin with. And then we just consider the value of the input density, so this quantity, and the derivative of this function. We consider them, so the log of this derivative as random variables on this probability space, so the unit interval with Lebesgue measure. And then we postulate that these 2 random variables have a covariance 0. So that's one way. You could say maybe that's not enough. We also want, maybe we want to also postulate the covariance of other functions of this vanishes, but it turns out this is enough for our purposes. because we can prove that if this covariance is 0, and then we look at the same quantity in the backward direction. So now we take the inverse of f, and we take the density over y, then it turns out that this thing is violated. So this covariance will be strictly positive in the backward direction, which just formalizes what I just said, that this value of this density will be large wherever this function is flat or wherever the inverse function has large derivative. So that's nice, and it can also be analyzed in terms of information geometry. But yes, yes.
Normally we don't take covariance over probability. It was the first time that I saw that someone got covariance. So the arguments are
So it's yes. So it's so the question is covariance over probabilities is a strange thing where we normally don't do. I completely agree. But I think if with these definitions, it's mathematically perfectly fine. So in this case, Px is just a function, it's a density function. So every function on a probability space is a random variable. So we just have to define what is the probability space. In this case, is 0, 1 with Lebesgue measure, so just the standard integration measure. And what are the functions? So now this could be anything. You can even forget that this came from a probability. That is the density of a probability. So at this point, it's just a function. And then this is perfectly well defined. And the reason for this is, the strange thing is we want to have an independence measure not of two random variables. So normally we talk about independence of two random variables, and they might have a joint distribution. But in this case, we talk about independence of the distributions themselves. So it's kind of on one level higher. In a sense, that's why we have to turn these probabilities first into functions. And then we can, on top of those, then we can, in a way, reason about properties of these distributions rather than properties of random variables. So I hope that made sense. Otherwise, I'll try to tell you again afterwards in different words. But I think mathematically, it's all fine, even though I agree it's a little unusual to do it this way. Okay, and one can also analyze it in terms of information geometry, and it turns out that the independence actually is equivalent to a certain type of orthogonal decomposition between these Kullback-Leibler divergences. So something becomes what they call a Pythagorean triple in the space of probability measures, in the sense that the irregularity of the observed output density, which is this one, so the deviation between the observed output and a uniform output, can be decomposed into a sum. So certainly if this thing looks irregular, it can have two reasons. One is that this function somehow is complicated or irregular, or whatever we feed in at the beginning is already irregular. Now, if these two things are not independent, then the irregularity of this one could compensate for the irregularity of that one. So then not all the irregularity is still there, present in the output. But it turns out if this and this are independent according to our definition, then the output irregularity is exactly the sum of two terms, and one of them is the input irregularity, so the KL divergence between the input density and the uniform input, and the other thing is, in a way, the irregularity of the function, and this is the divergence between a uniform output and the output that we would get if we feed a uniform input into this function. So that's one way to measure the irregularity of the function. So that's sort of one example of how we can define this strange concept of independence between two probability distributions viewed as objects and not as distributions of random variables. And one other way is to try to capture things in terms of algorithmic or Kolmogorov complexity. And I just want to talk about this briefly because I think I have also a nice example in terms of physics building on this. It goes as follows. So I've or maybe to begin, I should first say, so far I've talked about causal structures and statistical structures, and about links between causal structures and statistical structures. And of course, machine learning nowadays is all about statistics. But I think, and I think this is one of the things I learned from you. I think the causal structure is actually the fundamental one, and the statistical structure is just an epiphenomenon. So the causal structure captures the physical mechanisms in the world that generate dependencies, statistical dependencies in the first place. So statistical dependencies, they don't fall from heaven, they come from somewhere, and they come from underlying physical causal mechanisms. And in a way, you can say a statistical structure is an epiphenomenon that you get if you make the unexplained variables random variables. Now, at the same time, as you have noticed from the question in our little discussion here, it's somewhat awkward to talk about the independence between mechanisms, to talk about the information contained in a mechanism. And one reason why this is awkward is that a mechanism, if it's a deterministic function, then it can neither generate nor, if it's an invertible deterministic function, it can neither generate nor destroy information. So in a way, it also doesn't contain information. And this motivated us to look at this model here. And in this model, we have a DAG, a direct acyclic graph, and we put a computer program on each node. And the computer program runs on a Turing machine. So T is a Turing machine. P, A, these are the parents. And this is the computer program. And the computer program takes as inputs the results of the computer programs running on the parents. And we assume that all the programs are jointly independent in the sense of Kolmogorov complexity. So this means that each program is a bit string, and jointly independent means that if we jointly compress these bit strings, we don't save space compared to individually compressing them. So they are independent in this sense. And if one now builds this kind of structural equation model or structural assignment model, here it's clear, this is the output of computer program, it's not an equation, but it should always be viewed as assignments. So if we do this, then one can prove that this implies a causal Markov condition, just as in the case of graphical models and structural equation models, with the difference that effectively Shannon entropy gets replaced by Kolmogorov complexity, or statistical mutual information gets replaced by algorithmic mutual information. So in a way, we get a theory of graphical models which is analogous to the statistical case, but it also has some differences. It applies to individual objects in principle, up to the fact that Kolmogorov complexity is only defined up to a constant. And also, it's interesting that in this case, the independence of noises that we usually require and the independence of mechanisms actually coincide, because in this case, the programs play the role of the noise terms, you could say. But it's interesting to see this as an example that the causal structure is the fundamental one, and this can have sort of observable implications either in terms of statistics, if you are willing to make statistical assumptions and statistical distributions over noise terms, or it could have other kinds of implications that can be measured with other means, not statistical means, but in this case, means of compression length, etc. And if you think there's an interesting application of this independence principle for thermodynamics, and I can illustrate this with a little thought experiment. And in this thought experiment, we assume we have a beam of particles. So we think of this as the cause. And this beam of particles is now scattered at some object with non-trivial shape. And we think of this object or the scattering at this object as the mechanism. Now then the outgoing beam, so the particles as they are after they're reflected, certainly contains information about this object. And this is why vision is possible in the first place, right? Because what we see, what we measure in the end are the outgoing photons, and they have to contain information about the object where they have been scattered. Otherwise, we wouldn't see the object. Now, we all know from physics that microscopically, the time evolution is reversible. So it's somewhat strange that even though actually everything should be reversible, the photons only contain information about the object after the scattering. So why is it the case that they only contain information afterwards? In other words, why you could say, why do photographs show the past rather than the future? And you could say the reason is this independence principle. And one can formulate it in terms of algorithmic independence. And to do this, suppose that S is the initial state of the system, and M is the system dynamics. And we do it very simple. We just say we apply it for a fixed time, so it's not indexed by time. Let's say this is sort of one step of applying the system's dynamics. And then we will postulate that the initial state and the dynamics are algorithmically independent. So that means, in particular, sort of the shape of the incoming beam is independent of how the object looks. So that's a non-trivial assumption. It won't be true after the scattering, right? Because the outgoing beam is not independent of the shape of the object. So this is where an asymmetry is introduced, but it's a reasonable asymmetry. So you assume that the initial state and the dynamics don't know anything about each other. And we assume that this is true in terms of algorithmic information, so in terms of Kolmogorov complexity or compression. Then one can prove under this assumption that the Kolmogorov complexity is non-decreasing. So this means that the entropy, I mean, quite a few physicists in modern physics consider Kolmogorov complexity an interesting formalization of physical entropy. So it means that the entropy of the state monotonically increases, not strictly monotonically, but it monotonically increases. And that's this is the second law of thermodynamics. So that's what gives us the thermodynamic arrow of time, provided we accept Kolmogorov complexity as a sensible measure of entropy. So this concludes the part about independence, this independence principle, independence of a cause and mechanism, or independence of different mechanisms. But I promised you two methods, so I want to briefly tell you about the second one. And this is now going back to the statistical case. It also uses assumptions about the mechanism, but much more simple-minded assumption. In this case, the symmetry is broken by assuming that the noise only acts in an additive way. So the effect is not just a function of the parents. In this case, that's just one parent, only a two-variable problem. So it's not just a function of the cause and noise, but it's a function of the cause plus an additive noise. So that's a particularly simple setting. As before, we have to assume independence of the noise terms. X is the cause, it's identified with the noise terms. So suppose we have data generated by such a model. Can we decide if X causes Y or Y causes X? In other words, when is it the case that if data was generated like that, we can come up with a backward model that takes exactly the same form and explains the same joint distribution? And one can prove that in the generic case, roughly speaking, if either this function is nonlinear or if the noise is non-Gaussian, then there is no such backward model that explains the distribution generated by this forward model. So in the generic case, this model is not reversible in that sense. So if we are willing to assume that the noise is additive, then in the generic case, we are able to identify what is cause and what is effect. And we've applied this in the various domains. We've also applied it to a time series and also to deciding the direction of time in a time series, which was also kind of an interesting application. And we've collected the benchmark data set with a number of cause-effect pairs. And people have used them to benchmark all sorts of methods by now to decide between cause and effect. I mean, people have also done brute force machine learning methods that somehow train directly on plus minus one labels whether a data set is causal or anti-causal. So there's quite a bit of work on this now. So I want to switch gears a little bit and ask the question whether causal knowledge can help machine learning and where it could help. And maybe before I get into this, I wanted to ask how much more time should I use? Okay, so I think I will be able to talk at least about two of them, and hopefully maybe also about the last one. I mean, I wasn't planning to go through all of them, so don't worry, I'm not going to start rushing you through. The first one is, I think, an interesting connection between causal structure and the possibility or impossibility of certain machine learning scenarios. And I want to talk in particular about semi-supervised learning. And to do this, I first want to introduce a bit of terminology. The terminology is very simple. I will call certain learning problems causal and certain learning problems anti-causal. And it will simply depend on whether our direction of prediction. So in machine learning, we train a system to predict outputs based on inputs. So if this direction of prediction is the same as the underlying direction of causation, I'll call a problem causal. And if it's the opposite, I'll call it anti-causal. It turns out there's a lot of anti-causal problems actually in machine learning. There's also problems that are confounded. I don't talk about this right now. So let's say the world is simple. It's either causal or anti-causal. And here I have two examples of each. The first one is an example from splicing, or no, actually from reading. It's not splicing, it's reading of information from mRNA. And if we wanted to sort of predict from mRNA, then the peptide chain, as it's read off by the ribosome, it's causal because we know there's a mechanism called the ribosome that actually implements this procedure in reality. But the mechanism is so complicated, people don't understand it, so it still makes sense to try to learn it. Whereas here, the other example, handwritten digit recognition, in this case, we're given the image and we want to predict the class label from it. We would think of this as an anti-causal problem because if you think about how the data were generated, someone thinks in their head, I want to write the digit 0, and then a complicated motor program starts, and as the final result, you have the written digit 0, but that's an effect of a categorical variables that somehow happened in your brain. So that's an anti-causal problem. So whenever we do machine learning, supervised machine learning, I should say, we want to learn a mapping from X to Y. In other words, we want to estimate certain properties of the distribution of Y given X. So these properties could be just the conditional expectation of Y given X. It's also called the regression. Or it could be that we are interested in where this conditional probability is larger or smaller than 50%. That would be something like classification. But we're always interested in properties of this object. And now in semi-supervised learning, that maybe if you are interested in machine learning, you will have heard of, but otherwise I'll briefly say, semi-supervised learning, the idea is we may not have enough data, labeled data pairs X, Y, so we might not have enough pairs. We may have a lot of additional data just from X. Maybe they're cheaper because nobody had to label them. So suppose you have a lot more data sampled from P of X, and you somehow want to use this to improve your estimates. So you have more data from P of X, and you somehow want to use this to get more information about P of Y given X. So that's one interesting problem. Another interesting problem is something called covariant shift adaptation. I think I won't talk about this one now. But semi-supervised learning, so we want to improve this estimate. Now let's look at the two scenarios, causal, anti-causal. So here in the causal setting, suppose we still make our assumption from before that the input distribution viewed as an overall object again has no knowledge and vice versa about the conditional distribution of Y given X, so the mechanism. That's our favorite independence assumption. Suppose this holds true. Now you're interested in this object or properties of this object. Now I give you additional data from this object, but by assumption, this object knows nothing about this, then also the additional data should not help you. And interestingly, this is also what we find. So we didn't do any experiments on this, but we looked at a number of benchmarks that other people had run on semi-supervised learning, running their favorite algorithms, and we didn't find a single case where people managed to improve prediction on a causal learning problem using semi-supervised learning. We found a lot of cases, however, where people managed to improve predictive performance on anti-causal problems. And why is that? Well, in the anti-causal setting, now the roles of X and Y change, which means our independence assumption is between P of Y and P of X given Y. So these are independent, and as I mentioned before, in an admittedly very simple scenario, but it was this case here. I was telling you before, if we are willing to make the independence assumption in the forward direction, then in this simple setting, the independence is provably violated in the backward direction, because this is strictly larger than 0. So in the backward direction, we will actually provably have a dependence between these two objects, which means that if we have additional information about this thing here, so we have more input data, then actually that should in principle also help us to get a better estimate of this thing here. So in this setting, semi-supervised learning should be possible, and we find this in other people's results. And also we find that if we think about this problem from this causal point of view, a lot of the explanations that people have put forward to justify why semi-supervised learning works in the first place suddenly make more sense, I think, because all of these assumptions that we found can be viewed as assumptions linking these two objects. So there are always assumptions that link the input distribution, the input of the learning system, to the conditional. So for instance, there's this thing they call the cluster assumption, which simply says, let's assume the input density is clustered, and whenever we are within one cluster, the output label doesn't change. There's some other ones as well. So that was quite reassuring. And now I want to move to another example, which has been my favorite example in recent years, because I'm quite interested in astronomy. And so I appreciated this opportunity to work together with some very good astronomers at NYU over the last years. We worked together on this data from the Kepler Space Telescope. And this is a case where causality or causal modeling has very much inspired the model that we then built, which led to some improvements. And so this is a space telescope that's orbiting Sun. So it's not orbiting around Earth, but around Sun on an Earth trailing orbit, and staring at the same patch of Milky Way for several years. And this telescope, named after the astronomer Kepler, I want to mention, who was educated in my hometown, Tübingen, observed 150,000 stars over 4 years. So every observation is a bit of, almost all of them are exposures of half an hour. So we get a time series of brightnesses, and I think this is one of the most fascinating data sets available in science. And Kepler is looking for exoplanet transits in these light curves. So this is now a light curve, idealized light curve of a star. And we're looking for these dips in the light curve, and they can happen for all sorts of reasons. But one of the reasons is if a planet passes through in front of the star. So we have to be very well aligned with that solar exoplanet solar system. If you think about Earth, if you go out into space, you have about a 0.5% chance of seeing this if you go to a random direction in the galaxy, and you will see it once a year. So you have to observe for quite a while. And in the case of Earth and Sun, diameter of Earth is about 1% of the diameter of Sun. And then in terms of area, you have a factor of 10 to the minus 4. So the signal would have roughly the magnitude 10 to the minus 4. So it's relatively small, and often it's orders of magnitude smaller than the influence of instrument errors. And that's the problem. So what do we do about these instrument errors? Now, in reality, we observe not just one light curve, but a whole set of light curves for each pixel of this camera. So the light from one star might be smeared out over several pixels. So all these pixels belong to the same star. For each of them, we have a time curve. This is 3 months. And these curves are then affected, or what we measure is affected by at least two things. One is the quantity of interest, so the actual brightness of the system of star and sun, of star and planet. And the other one is the effect of the noise. Now, this instrument we assume to be independent of this star, and we observe this y, this vector y, or time series vector. We would like to reconstruct Q. Seems hard, seems impossible. However, we are measuring other stars at the same time. So we have a lot of other stars, and if we look at these, there's actually two aspects of these other stars that are crucial. One is they have no causal link to our current star of interest. So these things here might be light years apart, and they're measured using the same instrument. So they are, in terms of graph language, you could say they are half siblings. They share one parent, and then there's another parent that's different. So we've developed a method which now removes the effect of the instrument using effectively additive noise models, like the thing that I talked about before. And then when we combine this with an efficient method to search for light curves, this led to the discovery of about 15 new exoplanets. And just to give you sort of the humorous analogy of what the method does, not to be taken too seriously. So here you see a picture of 5 siblings. And there are actually some statistics that say up to 20% of all children have a father different from who they think is their father. And I'm sure it's not the case in America, but I did this picture while I was living in England. So in England, whenever something like this happens, the prime suspect is the milkman. So we call this the milkman problem. So now the milkman problem, however, is not to reconstruct which child is the milkman's child. The milkman problem is a bit harder. We would actually like to reconstruct the face of the milkman from the face of all siblings without having seen the mother. So that's a non-trivial problem. And the basic idea will be for each child in turn, we try to explain how this child looks as a function of the other children. And this kind of explains away everything that comes from the mother. And then the residual will say, this is our guess for how the milkman looks. And this can be formalized. So we have here a simple causal graph. A few assumptions have to go into it. So I already told you Q. So in fact, the assumption that we will use is that Q is independent of X. So the star that we're interested in is independent of the measurements of the other stars that we have made. So the basic idea then will be we perform a regression of the observed quantity on all the other observed quantities. The only reason why this is possible, why we can do better than chance, is the effect of the noise. And then we will remove this regression, so the conditional expectation, from Y to reconstruct Q. And if we're willing to make an additivity assumption and one more assumption, then actually in certain sense, this is actually the optimal thing to do. And I'll formalize it like this. So first of all, we have the additivity assumption. So we have to assume that the observed star is the sum of the unobserved quantity plus some function of the noise. Could be a complicated function. We don't have to know this function. So that's the first assumption. And the second one is that all the information about the effect of the noise, so everything, this is the thing we want to remove, f of n. So if everything about f of n should be somehow there in the other stars, in the sense that there exists some function of the other stars such that f of n is equal to that function. We will not know this function in practice, but if this is the case, then all the information is around. And if that's the case, then somewhat amazingly, I thought initially, it turns out that if we now do this thing that I just said, so we take the observed quantity, we just remove the regression on the other ones. So that's now our estimator. Turns out this is equal, it's an equality of random variables, almost surely, is equal to the unobserved quantity up to an offset, so up to its mean. We cannot guess the mean. So that's nice, and we can even generalize this. We can remove this assumption if we want, so we don't have complete information. If we remove that assumption, we get a weaker result, which contains the previous one as a special case, and the weaker result says that our estimate, so this thing here, so we take the observed star, we remove everything that we can explain in terms of the other stars. Our estimate deviates in a mean squared sense from the optimal thing, which is the other star up to its offset, by this quantity, which is the expectation of the conditional variance of f of n given x. So maybe that's a mouthful. It just means if x allows a very accurate prediction of f of n, then this variance will be small. If x allows sort of contains all information about f of n, this will be 0. So I think I'll have to move on. So we also have some results about when we get perfect recovery, depending on how the other stars, basically the results say if the magnitude of the other stars goes to 0, so in a sense we observe the noise directly, or if we see a large number of other stars that are independent from each other, then we get perfect recovery. And the method works quite nicely. So this is what the astronomers know. So this is like a raw time curve with a big trend. This is what the astronomers do with a pipeline of multiple stages involving PCA and all sorts of hacks. Here you see the exoplanet transits, and this is what our system automatically does. So it's a sort of nice and clean signal. The transits are still there. And you can also sort of statistically validate that red are our results, black the astronomer's standard. So in all the different sort of brightness buckets of stars, we seem to do better. And we have discovered some nice exoplanets. We're trying to apply similar methods currently together with gravitational physicists in the domain of gravitational wave physics, which I think is equally fascinating, or maybe even more, from a physics point of view, even more fascinating problem. I won't talk about that. We also, I will also skip this thing here. It's about a link between causality and fairness. And maybe I'll just talk a tiny little bit about this in the last 3 minutes or so. So this is about this dream that so the idea is we have some kind of model in our brain that we learn of the world, and we learn all the time, and we manage to merge all the new knowledge into our model, and we learn a model which also allows us to simulate the world, to reason about what will happen if we intervene in certain ways, a model that allows us to do counterfactual reasoning. So I think this should be the ultimate goal of statistical machine learning, even though currently this is not really being done. So we should learn this from multiple tasks in multiple environments. We should probably, I think, use this kind of prior that we're looking for independent mechanisms, because independent mechanisms they have this nice property that you have this modularity, that certain systems can be trained from multiple tasks because they are reused across tasks. So you don't have to get an infinite data set for every new IID task that you get. I think which wouldn't be scalable in practice, and which is not how animate learners work. So as a very simple example of something that we're trying to do is, we are trying to build a system to learn independent mechanisms that operate on digits. So in this case, we have data, 100 digits, the favorite data of all machine learners. And we transform them by a set of different mechanisms. The mechanism could just consist of adding noise. It could be inverting the digit, or it could be shifting it in the image. And then we are given the transformed data, and we are trying to explain this data with competing mechanisms, in the sense that a transformed image gets fed in. Then we have different experts that compete for this data point and try to explain it in the sense of making it maximally plausible as a digit. So this works a bit like a gun, generative adversarial networks. So this is a model that learns to distinguish real data from fake data. So these experts, they try to undo the transformation that has been done to this digit in order to turn this into a maximally realistic digit. This gets driven by the discriminator. So whenever the discriminator detects something, the error gets propagated back, and that expert that did the job gets further improved on undoing that transformation. So they compete, they gradually specialize over time on different kinds of transformations. So they learn these different independent mechanisms. We find that in the training process, at the beginning, sort of all experts win equally often, but then gradually each expert specializes on one task. And then at the end, we have a system where we feed in these sort of randomly transformed images, and what we get out by just always applying the winning expert is a nice representation of these digits. And then if we use this as a preprocessor for a standard classifier that was trained on the original digits, not on the transformed ones, then we find that we get very fast, after sort of relatively few iterations of training, we get to almost the performance of the original system, even though we feed it with these harder digits. So I think I'll skip this a little bit and come to the conclusions. Overall, I like to think of a modeling taxonomy where we have a continuum from starting from statistical models, which can do certain things very well, like predict in an IID settings. They're not very good at predicting under shift and intervention. They don't help us think or reason, but they can be learned from data. That's the great thing about statistical models. They usually don't provide physical insight or don't help us understand the predictions. Now, on the other extreme, I was originally trained as a physicist. You could say the other extreme is a differential equation model. It's the most detailed model of the world that we could build. We usually can't do it, so we usually don't know how to learn it from data. But if we can do it, in a sense, we could do everything. We could solve all sorts of problems with it. So in a way, in principle, one can argue about details, but in principle, everything should be possible. Maybe it's too complicated. I think of causal models as something in between. So this the notion of causality gives us a very useful abstraction of the true underlying physics. In a way, they can do everything that statistical models can do, but they also can predict under shift and intervention. And I think they will play a role in building these models that we will need for AI. Finally, this is the painting that I had on my first slide. Maybe you were asking yourself why I started with this picture. It's a painting by the English artist Lowry. He was famous for his depictions of the Industrial Revolution. And historians distinguish two industrial revolutions. So the first one began in the late 18th century. And it was triggered by a steam engine and water power. And the second one started about 100 years later, and it was driven by electrification. So if you want to think of it broadly, both industrial revolutions were about how to generate and convert forms of energy. And as a physicist, I should delete the word generate, because energy is a constant of motion. We cannot generate it, we can just convert it. So it's a conserved quantity. And if we now think about what's currently happening, some people say we're also in a revolution, and sometimes it's called the digital revolution or the big data revolution, but I think it really started already in the mid-20th century. And from my point of view, it started with the name of cybernetics. And in this, the notion of energy was replaced by information. So like energy, information can also be processed by people. But if you want to do it at an industrial scale, you need things like computers. And maybe to do it intelligently, you need things like statistics, machine learning, AI. And the analogy goes actually even further, I think. Probably information, at least that's what my physicist friends who are still doing fundamental physics are telling me, information is probably also a conserved quantity. I think people are still arguing, but that seems to be the case. So just like energy, so we can probably not generate it, just convert and process it. And I think it's fascinating that we are experiencing this changes currently, and I encourage everybody to think about this and engage into it. And I think causality will play a central role in this endeavor. Thank you very much for your attention. Yeah. Yes. Yeah. Yeah, I agree. Okay, so my answer would be on the level of physics, if you look at the underlying differential equations, each differential equation can be read causally, right? Because the left side tells you the change of this variable is a function of all these other variables. So there's a clear causal direction from the right-hand side to the left-hand side on the level of differential equations. Now, whether this implies whether a given, so now you start with a set of differential equations where causality is clear. Now you can ask the question: are there any kinds of macro variables, or is there any kind of abstraction of these differential equations for which I can sensibly talk about causal direction? And then I would think in the generic case, the answer is probably no. So I don't think that all possible macro variables that we will be able to come up with do fit into a causal diagram. So I think this abstraction will not always work. So I'm sure we can come up with lots of examples where it doesn't make sense. I mean, it's also related to this question: when does it make sense to talk about causality if time is not involved? A lot of people would even say causality without time. How can this be possible? So I think it's yeah. I'm not sure I get your point.
I have a question related to this.
Yeah.
We know that if you have the smoke coming from a chimney, you know which direction of time the time goes. Time follows the flow of the smoke. You rarely see the smoke coming back to the chimney.
Yeah.
But now, because this is a non-equilibrium situation.
Yeah.
How about if you take a picture or a movie of a Brownian motion in equilibrium? You run it backward. Could your system tell the direction of time?
If it's in equilibrium, then I would be surprised. If it's